Probably the most important principle that you will use in your work with simplifying radicals is this one right here, which says that powers of n and nth roots are inverse operations of each other. That just means that if you have a number and you apply a power to it, you can reverse the effect of the power by doing the nth root, or in this case the square root, and that brings you your 3 back again. If you have 2 to the 4th power and you want to undo the effect of the 4, you can 4th root, and that brings you your 2 back again. So stated symbolically, this principle says that the nth root of x to the n will bring you back x, and this is true as long as x is greater than or equal to 0. We'll talk about what happens when x is negative later. But this is a principle you've used in your previous work with radicals. For example, when you've been asked to simplify something like the square root of 24. Now, just a reminder that simplifying a radical means that we need to remove any nth root factors from the radicand. In this case, square root factors from 24. So we need to break up our 24 into factors, which we can do via a factor tree, or in this case, since the number is fairly small, 24, we can just think about the biggest perfect square that divides into 24, which is 4. So 4 times 6 is 24. And then we can apply this principle of radicals, which we've talked about in the past. If you multiply two nth root radicals with the same index, then you just multiply the radicands, a and b. So the nth root of a times the nth root of b will be the nth root of a times b. And this statement is true as long as these radicals are defined. So we can break our radical expression here up into root 4 times root 6. And remember, the root 4 is 2 squared. That's why it's a perfect square. And then we can apply the inverse principle we talked about at the beginning. The square root of 2 squared, that'll just be 2. And that'll multiply that 2 by root 6 for our final answer. Okay, let's just review an example with cube roots. So in this case, we'd be looking for the biggest perfect cube that divides into 16. Our perfect cubes, remember, we can think of them this way: 1 cubed, 2 cubed, 3 cubed, 4 cubed, etc. Which of these numbers, or do any of these numbers, divide into 16? Well, we can see that 8 does. So we can break our 16 up into 8 times 2. And then we can break up our expression here as the product of two separate radicals using this principle. And 8, remember, is 2 cubed. And here's our inverse principle showing up again. The cube root of something cubed, that'll just be 2. The cube root and cube knock each other out. They're inverse operations. So this section becomes 2, and this section stays as it is, the cube root of 2. So 2 times the cube root of 2 is equivalent to the cube root of 16. So there you have some examples of applying this important principle in reducing radicals. What happens, though, if this value is negative? Because all of the examples I have previously talked about had this value x being a positive value. Does anything change if x is negative? Well, sometimes yes, sometimes no. So let's just explore this a little bit more. Let's take n equals 2. So that would be a square root. And now instead of using a positive value here, let's use a negative value. And so what does that reduce to? You would probably think that the answer would be negative 3. But there's some things that happen along the way here. To work this out, negative 3 squared, that's going to be positive 9. And then to evaluate this expression, we need to remember that this radical represents the positive or principal square root of 9, which would be not negative 3, but positive 3. In other words, the absolute value of negative 3, which is 3. Remember, absolute value just means that the number that goes in, whether positive or negative, comes out positive. All right? So in general, the square root of any value of x squared is not going to be x, but it's going to be the absolute value of x. The same thing will happen whenever you have an even index. If we had the fourth root of negative 2 to the power 4, then that would be the fourth root of negative 2 to the power 4 would be 16. And since we have an even index, we know that 16 has 2 fourth roots, and this symbol represents the positive root, which would be not negative 2, but positive 2, the absolute value of our x. This was our x to start with, and this is our x here, but our answer is the positive of that, which is 2. So the fourth root of x to the fourth, where x is any real number, will not just be x, it will be the absolute value of x. And this will be the case whenever you're dealing with even indexed radicals. When you're dealing with an odd index, this will not be a problem. So if we had the third root of negative 2 to the power 3, again, if we work this out, negative 2 to the power 3 will be negative 8. And since an odd indexed radical only has one answer, the answer is negative 2. Our value of x that we applied the power to is what we get as our output. So the cube root of x cubed will be x. So to generalize, we're saying that the nth root of x to the n is the absolute value of x if n is even and x is any real number. If n is odd, then our nth root of x to the n will just be x. All right, so the upshot of all of that is that you need to be particularly careful and mindful when you're simplifying radical expressions involving negatives in the radicand, because negatives in the radicand can affect whether an expression is defined or not, and it can also affect the simplification in that sometimes absolute values will come out in the simplification. So there's all these things you need to be constantly thinking about as you do your simplification. All right, here's an example. We want to simplify this expression, and we're told that the variables represent positive numbers. Now, this information is important because it can affect whether our expression is defined or not. If we just look at this, we have our 25 times our x, which is positive, times y, which is positive, and so y squared is positive. We have the multiplication of numbers which are all positive, which means we're square rooting a positive number, which we know we can do. We know that would be defined. All right, so full steam ahead. We can simplify this by considering each factor separately. Let's break up our radical to separate parts. Our 25, the square root of 25 is 5. Our square root of x, there's no perfect squares there. And here we have the square root of y squared, which we can write y for that. We don't need absolute value y, because y is only a positive number in this example. And therefore my expression reduces to 5 times y times the square root of x. Now we have the same expression, but we're told that the variables represent any real values, which means that x and y could be positives or negatives. So again, the first order of business should always be considering whether this expression is defined or not. This is a square root, which means that we need a number that is 0 or positive in the radicand. So we have 25 times x. Now, if x is negative, is that going to cause a problem? Let's look at our y. Our y, what if our y was negative? If our y was negative, we'd have a negative squared, which would make that positive. So we would then have 25 positive times x negative times y squared positive. We would have a negative under the square root sign, which we can't have. So our first order of business is to put a restriction on this. This expression will only exist if x is greater than or equal to 0. Y can be negative because you're squaring y, so the value of y that's negative will become positive. But we need to have this restriction as part of our answer. Okay? All right, now we can break up our radical expression into its component parts, as we did above. Does anything change? This is 5. This is the square root of x, with the condition that x must be positive or 0. And the square root of y squared, because y can be a negative, we know that's going to be the absolute value of y. And so therefore our expression reduces to 5 times the absolute value of y times the square root of x.